Imagine heating a gas inside a sealed cylinder. Heat flows into the gas. The piston begins to move. The gas does work on its surroundings. But here's the mystery. If some energy entered the system and some energy left the system, what happened to the rest? Did it disappear? Can energy ever be destroyed? Or is it hiding somewhere inside the system? Every engine, every battery, every living cell, and every chemical reaction follows the answer to this very question. These systems may seem completely different, but they're all governed by one fundamental idea: internal energy. It's the missing piece that connects heat, work, and energy, and it allows us to understand one of the greatest principles in science, the first law of thermodynamics. But before we discover the first law, we first need to answer one simple question. What exactly is internal energy? Because if we don't know where energy is stored, we can't understand how it changes. So, let's get started. In Episode 1, we explored the basic language of thermodynamics, the system, the surroundings, the state of a system, and the variables like pressure, volume, and temperature that describe that state. Then, in Episode 2, we discovered the two ways a system can exchange energy with its surroundings, heat and work. But that leaves us with a deeper question. If energy is constantly flowing into and out of a system as heat and work, where does that energy actually go? What happens to it once it enters the system? That's exactly the question Episode 3 is here to answer. That energy stored inside the system has a name: internal energy. And the rule that governs how it changes is the first law of thermodynamics, which, spoiler alert, is really just the law of conservation of energy wearing a lab coat. But before we understand how internal energy changes, we first need to understand what internal energy actually is. Consider a system of gas trapped inside a cylinder. Let's zoom into the system. What do you actually see? Not pressure, not temperature, not volume. You see millions upon millions of tiny molecules, moving, colliding, vibrating, and in many cases, rotating. Every one of those molecules possesses kinetic energy because it's constantly moving, vibrating, and rotating. It also possesses potential energy because of the attractive and repulsive forces between molecules, as well as the chemical bonds holding atoms together within each molecule. But here's where it gets interesting. Instead of looking at the energy of just one molecule, thermodynamics considers the combined energy of billions upon billions of them. That combined microscopic energy is called internal energy, represented by the symbol U. It is the total microscopic energy stored within a system due to the motion and arrangement of its molecules and atoms. But knowing what internal energy isn't enough. To understand why it's so useful in thermodynamics, we need to look at one of its most important properties. Internal energy is a state function. That means it depends only on the current state of the system, its temperature, pressure, and composition, not on the path taken to reach that state. Whether you heat the gas quickly or slowly, whether you do it directly, or in 5 separate steps, if the gas ends up at exactly the same temperature, pressure, and composition, its internal energy will be exactly the same. And here's another interesting fact. Internal energy isn't something unique to gases. Every substance has it. Whether it's a cup of hot coffee or a block of ice, it possesses internal energy. Even your own body is constantly storing and transforming internal energy through thousands of chemical reactions every second. As long as matter exists, its particles are always moving and interacting, which means every material stores some amount of internal energy. Now, you might wonder, if every substance has internal energy, can we actually measure its exact value? Surprisingly, the answer is no. We can almost never calculate the absolute value of internal energy because it includes countless microscopic forms of energy: translational, rotational, vibrational, electronic, chemical, and even nuclear energy. But that's perfectly fine, because in thermodynamics, we almost never care about the absolute value of U. What really matters is delta U, the change in internal energy. And that is something we can measure, calculate, and predict. So now everything comes together. When heat enters or leaves a system, and when the system does work or has work done on it, How exactly does its internal energy change? That's precisely what the first law of thermodynamics tells us. To answer that, let's return to our gas-filled cylinder. Imagine heating the gas inside this cylinder. As the gas absorbs heat, energy enters the system. At the same time, the gas expands and pushes the piston upward. That means the gas is doing work on its surroundings. So now let's think about energy. Some energy entered the system as heat. Some energy left the system as work. Naturally, the energy remaining inside the system must be energy entering minus energy leaving. That's exactly how the internal energy changes. This simple idea is the heart of the first law of thermodynamics. It is nothing more than the law of conservation of energy applied to a thermodynamic system. Energy cannot be created. Energy cannot be destroyed. It can only move from one form to another. So far, it was the idea behind the first law of thermodynamics in words. But in science, ideas become far more powerful when we can express them mathematically. And you'll notice, the equation is much simpler than it sounds. The law can be stated as an equation where delta U equals Q minus W. Delta U represents the change in internal energy. The symbol delta means change in. Q represents the heat transferred into the system. And finally, W represents the work done by the system on its surroundings. Like heat and internal energy, delta U is measured in joules. Now, to use this equation correctly, there's one important detail we need to understand: the sign convention. Whenever heat enters the system gains energy. So we write positive Q. Now imagine the system loses heat to its surroundings. Energy is leaving the system. Here, Q becomes negative. Now let's look at work. Suppose the gas expands and pushes the piston upward. The system is using its own energy to do work on the surroundings. Since energy is leaving the system, W is positive, and it is subtracted in the equation. As a result, the internal energy decreases. Now imagine the opposite situation. Instead of expanding, the gas is compressed by pushing the piston downward. This time, the surroundings are doing work on the system. Energy is entering the system through work. So in this case, W becomes negative. And because the equation is delta U equals Q minus W, subtracting a negative value means the internal energy increases. The rule is actually very easy to remember. Heat entering increases the system's energy. Work done by the system decreases the system's energy. Everything follows naturally from that one idea. Now comes the interesting part. This single equation can describe several different thermodynamic processes. Depending on what happens to heat and work, the equation takes different forms. Let's explore each case one by one. Imagine a gas sealed inside a pressure cooker, which is a rigid steel container. Now think about what happens if we heat the gas. The gas certainly gains energy. Its temperature rises. Its pressure also increases. But can it push the walls outward? No. Since the walls cannot move, the volume of the gas always remains the same. So work done by the system is zero. If we substitute this value into equation, delta U equal to Q. This type of process is called an isochoric, or constant volume process. Every single joule of heat you supply goes directly into raising the internal energy, which, for a gas, mainly shows up as a rise in temperature. This is exactly why a pressure cooker's contents heat up so fast and pressure builds rapidly. All that heat has nowhere else to go. But what if the volume is allowed to change, while another property remains constant instead? Imagine an ideal gas inside a cylinder with a movable piston. This time, we heat the gas very slowly, allowing its temperature to remain constant throughout the process. Such a process is called an isothermal process. Now here's the fascinating part. Even though heat is continuously entering the system, its temperature never changes. So where does the supplied heat go? It isn't stored as additional internal energy. Instead, it is immediately used to push the piston outward. In other words, the heat supplied is completely converted into work. For an ideal gas, the internal energy depends only on temperature. Since the temperature remains constant, the internal energy also remains constant. Therefore, delta U equals 0, and the first law becomes Q equals W. Every joule of heat added is converted into an equal amount of work. So far, heat has been entering the system, but is it possible for a gas to expand without receiving any heat at all? Surprisingly, yes. Imagine wrapping the cylinder with a perfectly insulating material. Now the system is completely insulated from its surroundings. No heat can enter. No heat can leave. This is called an adiabatic process. Here, Q equals 0, but suppose the gas still expands and pushes the piston outward. If no heat is entering the system, where does the energy required to do the work come from? The answer is its own internal energy. Substituting Q equals 0 into the first law, we get delta U equals minus W. This means that as the gas performs work, its internal energy decreases. That's why a rapidly expanding gas often becomes cooler. It is using its own stored energy to perform work. Now we've understood the theory. We've seen how energy behaves under different conditions and how the first law gives rise to different thermodynamic processes. But science becomes truly fascinating when we recognize it outside the textbook. Every car engine is a machine converting heat into work using exactly this law. Every refrigerator uses work input to move heat against its natural direction. Even your own body follows the first law. The chemical energy in food converts into internal energy, heat you release, and the work your muscles do. The first law of thermodynamics is really just telling you can move energy around, convert it from one form to another, but you can never cheat the total. Nature keeps a perfectly balanced ledger. But here's something fascinating. The first law tells us how much energy is conserved. It keeps a perfect account of every joule. Yet it doesn't answer another equally important question. Just because a process doesn't violate the first law, does that mean it can actually happen? For example, why does a hot cup of coffee naturally cool down but never become hot on its own? Why does perfume spread throughout a room by itself but never gather back into the bottle? If energy is always conserved, why do some processes happen naturally while others never do? To answer those questions, we need another fundamental law of nature, the second law of thermodynamics. And with it comes one of the most fascinating concepts in physics, entropy. We'll uncover that mystery in the next episode. Until then, if you enjoyed this video, don't forget to like, subscribe to Decoding Education, and share it with someone who thinks thermodynamics is just about difficult equations. Because as we've seen, it's actually the story of how energy governs our entire universe. I'll see you in the next episode.